What's up, mga ka-Che? It's Edil here, and I'm back with another chemical engineering principles lesson. So after filtration, we will be going back to um, chemical engineering principles, and now we're discussing one of the hardest uh, topics in the unit operations, no, in the transport phenomena, which is the mass transport. Yeah, mass transfer, diffusion. Yeah, it's really difficult. I really don't like this subject. Yeah, because I also have a experience back when I was in college that this particular question in our final exam was the only item I could not answer because I forgot how to solve it. Yeah, so I want to thank you for your support, no, in the last video, no, the filtration, and also for the biochemistry lecture for the University of Santo Tomas fourth year chemical engineering students. So I really thank you for that. And yeah, I want to thank my teacher, no, in helping me solving this. She is Engineer Lara May Lumbres of Quantum Review Center. Okay, so she really taught me. I really had fun consulting with her on this problem. So some of this I can't solve, so I reached out to her for help. Okay, so without further ado, enough for the shoutouts and introduction, no? So let's begin with our lesson for this video. Okay, so let's begin with the diffusion now, no? Okay, so let's start with the first question. So we change color here. Yeah, so the enrichment of ethyl alcohol in the vapor phase from aqueous ethyl alcohol solution during rectification is an example of, no? So when you are purifying, no, you're boiling of ethyl alcohol, diba, from a aqueous ethyl alcohol solution during rectification. Rectification is you can find this in the distillation, no, the upper part of the distillation section, that's the rectification, and then the stripping section is on the bottom. Okay, so this is equimolal counter-diffusion. Okay, equimolal counter-diffusion is that when two uh, species, no, when two species exchange from one concentration to another, and then also from this. So I'll explain that later. Okay, so yeah, if you know equimolal counter-diffusion, unicomponent diffusion, it should be it should not be new to you. Okay, so number two, the diffusivity of a binary system as given in the equation of Fick's law. So Fick's law, you can find it in your Paris chapter 5. Okay, so it's usually measured relative to d. So this is volume mean velocity of the component A and B. So volume mean velocity, not mass mean velocity. Okay, so yeah. Number three, so molecular diffusion of A is yun, kanang number at 298 Kelvin. What will be the bulk velocity in centimeter per second if the diffusion flux relative to a stationary observer is 8 to the negative 7 gmoles per second per square centimeters. Okay, and the mole fraction of A is 0.015. Okay, so how do you solve this? So you can find this in McCabe. Okay, in McCabe. So this is in equation 17.4 in McCabe, no? So I'm using 7th ed nga McCabe, no? 7th edition ng McCabe. So that's the latest edition of the McCabe. So how do we solve this? So we have a diffusion, no? Diffusion J. So J A. Okay. and most of the time it is not measured an absolute, no, it is measured relative to a stationary observer, and that stationary observer is also the standard, the reference, no, the reference in which we can measure the bulk velocity. Okay, so we have this kuan formula, no, kava minus kavo that's kavo. Okay, so what that means, no? So JA is your molecular kuan kining flux. Okay, so this is 4 times 7 to the kuan, so negative 4 times 7. Then CAVA, this is your kuan flux this is your flux in the kuan, this is your ini, is 8. Yeah, that's relative to the stationary observer. This is 8. Okay, negative 7. And then we are finding now the VO, di ba? So VO at VO atong ginapangita. Okay? So if we solve for kavo, we have 4 times 10 to the negative 7, di ba? That's it's not right units for now. Okay, so we have, di ba, we have our temperature at 298 Kelvin and our pressure at 1 atm. Okay, so how do we get the C so that we can get the VO? Okay, CA, you can solve that by the molal density. No, molal density is P over RT. Okay, so you can use this formula, no? Or, di ba, wala pa man tayo, we don't have a CA man, di ba? So we have to find the molar fraction of A so that we can kuan nga that's the concentration of A, di ba? So this is total man. We can use Raoult's law for this. Nga, di ba? PA man PA. So we don't have PA, the partial pressure of A, but we can use the total pressure of A times the molar fraction of A in the gaseous phase, di ba? Using Raoult's law. Ini PP then RT. Okay, so we have a 0.015 times 1 atm, and then can use 82.057 centimeter cube atm and Kelvin per mole kana siya nga units. Okay, this is atm, and then you have a 298 Kelvin. Okay, so if you plug that kini siya nga dito, okay, we have so just plug it there, and then you can have your VO as 0.65 cm per second. Okay, so that's how you solve these kinds of problems that in one stationary observer. Okay, so that's how we can solve that. Number 4, diffusivity of component A relative to itself. That is DAA. Okay, so it has a physical meaning and can be measured. Okay, so don't think it has not, it cannot be measured. It can be measured. Okay, and Reynolds Analogy. So this is what I have mentioned in my heat transfer video. No, Reynolds Analogy, you can use that when NPR and your Schmidt number, okay, your Prandtl number and Schmidt number is equal to 1. Okay, so that's letter B. So number 6, the molar flux of component A in molecular diffusion is independent of, okay, molar flux of component A. This is independent of the mass transfer area. Okay, so just this is just look at the equation. Okay, so this is usually the equation of that. And then kung unicomponent, kay ln something. Okay, so number 7, dimensionless number that represents the ratio of the mass transferred by molecular diffusion to the total mass transferred. Diba? So, mass transferred by diffusion, o diffusive, empty, dayon bulk, total mass. So, total mass transferred. Okay? So, total mass transferred. If you search this, no, ang niya, ang dul-dul niya, the nearest to this is actually the Schmidt number. But Schmidt number is the opposite or the reciprocal of this. This is Schmidt number. We can find that later. Okay, but based on the choices, this is none. This is none of this. Okay. So yeah. Number 8, the molar diffusion of A relative to the stationary plane is a combination of what? Okay. So stationary plane. So if you read this in McCabe, so the answer is letter C, phase drift plus molecular diffusion. This is in chapter 17 of McCabe. So let's read it there. Number 9, Fick's law of diffusion gives the rate of diffusion based on, diba? Fick's law of diffusion. Please read that also, chapter 5 of your Paris. In the mass transfer area, okay, first part of your chapter 5 is for the heat transfer. So the later part, the second part is for the mass transfer. Okay? So this is number 9. Kung diffusion gani, mass transfer, you have concentration driving force. Kung momentum, diba? That is pressure driving force kung momentum transfer. And also if heat transfer, temperature driving force. Kung mass transfer, concentration driving force. Okay? So that's, remember that. Equimolar counter-diffusion means that the bulk in terms of moles is not moving. Okay? So that's it's not in terms of mass, ha, diba? So if you can see the JA unit, it's usually in kilogram moles per unit time per unit area. Okay, so that's one. So means that the bulk in terms of moles is not moving. Okay, because it's net magud siya. Okay. So the one is moving from this direction to the opposite, and then if you get the sum, so if their momentum, ano siyang 0. Okay? So siyang 0. Sige. Next, for a gas phase diffusion, unicomponent diffusion through a gas-liquid interface will likely occur if number 11, so one component is soluble and the other is not. Okay, so for example, you have a bowl, no? If you have a bowl of water diha, and then it is evaporating. Okay, it is evaporating. So the action here, and also if there is wind, no, air passing through, the mass transfer, no, mechanism or the direction of the mass transfer is from the liquid to the gas. Okay, so the air will pick up the water, no, evaporate the water, not the water condensing, not the air condensing to the water. Ano siya? So the air is not soluble in water. So that's how I think about it, no. If the one part of the it's not diffusing back to the first component, so that's unicomponent, isa lang, water is the only one who is going to the air. That's but for gas phase diffusion, this is liquid man din siya. But for gas phase diffusion, one component must be soluble and the other is not. Okay, because if you happen to do it, it will be equimolar na counter-diffusion if both components are soluble in the solvent. Okay? So number 12, the rate of mass transfer of component A through the interface in a turbulent flow system is less affected by, okay, less affected daw siya by the flow rate of gas and liquid. Basta, paano gani kung if it is turbulent na, it is not less affected na siya by flow rate of gas and liquid. Okay? Number 13, for a binary component, unicomponent diffusion, concentration profile of the diffusing component along the diffusion path is logarithmic na siya. Okay, if you can notice, no, in the later part of this video, you can see that the formula of unicomponent diffusion is naa siya ln. Yeah? And then for the equimolar counter-diffusion is walay ln. Yeah. Number 14, transport analogy among mass, heat, and momentum transfers is complete when, yeah. Number 14, this is letter B. No convective flux or phase drift is involved. Number 15, wetted wall column, usually used to determine mass transfer coefficient experimentally because the mass transfer area. Okay, that's the only thing that it can be measured accurately because you have the dimensions of the wetted wall column, so you can measure that accurately. So that's why this device is used for mass transfer coefficient determination. Okay, so yeah. Number 16 provides the basis for the quantitative description of the diffusional phenomena of molecules. This is kinetic theory of gases. Number 17, method of solute transfer, which involves rapid movement of large chunks of fluids in turbulent motion. Turbulent motion, okay, that's eddy diffusion. Okay, so itong mga bulyok if in Bisaya. Mga bulyok eddies. Okay, yeah. Number 18, ammonia being absorbed from air, letter B, into water is an example of, yeah, what is that example of? So let's letter B, component, okay, absorbed from air into water. Okay, so that's the water will not go from the solution into the air, but the ammonia is being transferred, no, from air into the water. Okay, water will not go back, or the ammonia will not go back to the air. Yeah, the ammonia will not go back to the air, but it's being absorbed by the water. Okay, and number 19, a steady state equimolar counter-diffusion, the following is true. This is letter B, diba? So both components are equal but opposite lang ang signs, but the net is zero. Wala siyang equimolal counter-diffusion. Number 20, the flux of A in unicomponent diffusion is different from that of equimolal counter-diffusion because of number 20, letter B, the bulk motion of the phase. Okay, bulk motion of the phase because for one unicomponent, only one component is moving from one place to another. Or as kung equimolal, so they will mix may tabo. And then the concentration, no, from one to another will be decreased. Yeah, if you have okay, so if you have this container, no, this is component A and component B. Then if you have a valve here, let's draw a valve here. Okay, if you open this valve, that allow them to make some time, the concentration of A here will be diminished, and also B will be diminished here, and then at such time their concentration will be somewhat equal, but the rate of molecular diffusion will be equal na. Okay, and wala na rin net, zero na rin. Okay, number 21 represents the total mass transferred to mass transferred by molecular diffusion. This is the Sherwood number na. Okay, this is the Sherwood number. This is the reciprocal of what we have said earlier. Number 22, measure of the diffusive mobility of individual molecules in the solution. That's diffusion coefficient. Katong dV, diffusivity. Yan. Okay, diffusion coefficient. Number 23, volumetric diffusivity of binary mixture. Okay, at yun, please read. And molar diffusivity of similar mixture is just we are asked to convert from a square foot per hour to pound mole per feet per hour. Okay, so let's do that. So number 23. So basically what they're asking is transform dV to dAd. So this is the volumetric na diffusivity, then mahimo siya molal na diffusivity. Okay, so how do we transform that? Just multiply dV with the molal density, and molal density you can get that by PRT. Yeah. So do that. dAd, dV we have 0.934, diba? 34 feet squared per hour times P. Pila tong P? We have 280 m. Then R, use the 0.731, no? I leave you the units. Units is cubic feet, atm per lb mole per Rankine, degrees Rankine. Okay? Sige. And then the temperature is 546 degrees Rankine. Okay? 40 degrees Rankine kini siya. 30 degrees Celsius. Just transform that to Rankine. And then you will have 4.687 times 10 to the negative 3 pound mole per feet per hour. Yeah, that's letter A. Okay, number 24. We have a technique for this, no? If you have this diffusivity at this temperature and pressure, and then suddenly you can the temperature or the pressure is changed from this to this, no? The diffusivity of benzene in air. So how can we do that, no? We have this technique, the Chen and Othmer equation, the technique. It's Chen and Othmer. We can do this. So dV kaning n, nu talang nu, n, and then you have dV old. Yeah, so this is the temperature, the pressure old over the pressure nu, and then the temperature nu over the temperature old raised to 1.81. Okay, so T is in absolute, no? Absolute meaning in Kelvin or in degrees Rankine. So just plug in play lang, there is no change in pressure, but you have the change in temperature, ba? 295, just just transform it to Kelvin and raise it to 1.81. You have 0.344 cubic feet square feet per hour, but we have no wala taan na in the feet per hour, but we can transform that to square centimeters per second, no? Let's transform that to that. So we have 30.48 cm over feet squared times 1 hour, then 30,600 seconds. You will get 0.089 square centimeters per second. So solving this kinds of problems, it really brings me joy. You get the satisfaction you get that the answer in the calculator is the same in the choices. So that's what I really felt in solving these problems. Okay, number 25, it's a bit complicated, but this is actually a equimolar counter-diffusion. So number 25, so you have your JA, di ba? JA. So but JA is actually the moles over area times the time, di ba? So we have the CDV, di ba? C, then actually C, then KC. Ano? But we can take this formula apart pag yun. So C, di ba, is actually P over RT, and KC from the film theory. Film theory is dV over Z. Okay, dV over Z. It's KC. So we can take it apart. So we have our C, our concentration, P over RT, which is really given to us na good. So we have Na, but 12, 0.12 grams per cubic centimeter, cubic centimeter, so na siya, 0.12 grams per cm cube. Dayon we have the diffusivity, diffusivity of alcohol, ini siya. Let's use that. 1 times 10 to the negative 5 cm per, and then the length is 0.15 cm. Then we have the area. So area is 100 square feet. Okay, let's transform that to square centimeters. Square. Then we'll have to transform the seconds to hours, and then the grams to pounds. Okay, so just to fit the required units. Okay, so Na is 5.89 pounds per hour, or 6 pound mass per hour. Okay, that's basically it. 6 pounds per hour. Okay, letter A. So number 6 is using the Chen and Othmer equation I taught you earlier, just read the problem and just use it again. Okay, so dVn, dVo pila man, 135 cm per s, then PO ba, wala man tayo kuan, so wala man tayo change sa pressure, but we have a change in temperature. We have 353, 298, 1.81. Then we'll have a 0.1834 cm per s. Okay, so that's the answer for number 26, letter A. Okay, so the last two numbers, no, siguro, before we end this video. Number 27, actually, it still requires you to use the Chen and Othmer equation. This is really easy. Just dVO n, diba? You have filament to 0.135 from the previous problem, and then 1/3, diba? Because of the change in pressure, but we have no change in temperature. Okay, so 1.81, just wala yapon, no change. So you have 0.045 cm² per s, but we have to transform that to square feet per hour, and then using I've shown you how to transform that, and then so the answer is the third A. Okay, so trust me, the numbers that you see in the choices are what I really got from the calculator, so you can be assured that you've got the right answer. Okay, so for the last number of this problem, last number of this video, no, number 28. So using the appropriate transport analogy, okay, transport analogy, estimate the mass transfer coefficient in feet per hour using the ammonia air water system in a wetted wall column, where the Reynolds number is 25,000, the Schmidt number is 1.8, and the average velocity of the gas is 1.2 feet per second. Okay, so how do you use the appropriate transport analogy? You can't use the Reynolds analogy here because as you can see, the Schmidt number is 1.8. Okay, so you can't use the Reynolds analogy. What we can use is the Chilton-Colburn analogy. Okay, Chilton-Colburn analogy, it looks like this. Good, KC and VAV, and then actually if you have the NPR, okay, the NPR here, it's still 2/3, okay, and then still you have CPG, okay, ayap na siya. Okay, so I can't really remember the form in the heat transfer nga part, but in the mass transfer nga part, it's this it's this structure. Okay, so, but and also we were not given the Prandtl number ba, so we have to assume it as 1. Okay, so para wala na siya, it will not bother us anymore. So what we have is the mass transfer coefficient, no? So kini muni siya ang gipapangita sa tuwa, Kc prime. Okay, Kc prime is the equimolal counter-diffusion mass transfer coefficient. Okay, so I'll tell you the distinction between the two in the next video. Okay, so we have the 25,000 nga Reynolds number. So use the Moody chart, no? Moody chart in chapter 6 of your Paris to find the fanning friction factor F, and this is what I found. F is equal to 0.0061. Okay, and then just substitute everything, so you can get the Kc, diba? So F, V Av, and 2 SC raised to 2/3. So 0.0061 times 1.2 feet per second, then 2 times 1.8 raised to 2/3, and then we are asked to feet per hour, diba? So just convert it directly na. So 3,600 seconds in 1 hour. You can see that it is 8.904 feet per hour. yeah, it really the exact numbers that you have in your calculator. You can use that in. You can see that in the choices. Yeah, that's how satisfying it is to answer these problems. Okay, so that ends the first part of the diffusion video. So we went a bit on with our 30-minute mark, but that's how I can do to really cram the answers into this video. Okay, so that's it. I'll hope I hope to see you in the next video. Please, if you haven't subscribed yet, um, I post my videos every week, no? So and then please subscribe and then ring the notification bell so that you won't miss a single upload of any of my videos. Okay, that's it. Bye.